Hello, welcome to this video. This is 1A.5 and we're going to talk about polynomial functions and their complex zeros in this lesson. Given a polynomial function in analytical form, we can easily find those complex zeros by breaking the function down, and we'll talk about how to do that in this lesson. Alright, we're going to go ahead and find all complex zeros, and then towards the back half of the lesson, might be in another video, we're going to sketch the graph of a polynomial function with those real zeros. So first of all, you may be wondering, what the heck is a complex number? Well, a complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is the imaginary unit. I equals the square root of -1. Okay, so that's very, very important, is that we have imaginary numbers and that makes it a complex number. Real numbers, I just want to go ahead and specify, real numbers are made up of two types of numbers, rational and irrational numbers. Rational numbers are any number that can be written as a over b, where a and b are integers. Rational, generally think fractional. 5 is an example of a rational number, and you may say, hey, that's not fractional. Well, 5 does have a denominator, it's just 1. Okay, so that's a rational number. 2/3, that's a rational number. -8, yes, rational numbers can be negative. And then irrational numbers are numbers that are non-terminating. We have square root of 6, you can have cube root of the cube root of 3, and then here we have 1 minus the square root of 5. So these are all rational numbers, irrational numbers, sorry. Then we have imaginary numbers, and there's two types of classifications, which isn't really a big deal, but it's just a slight distinction. You have pure imaginary numbers where we're made up of nothing but imaginaries, so 6i, -2i, square root of 2i, and then you have just imaginary numbers where they're in this form that we mentioned up here, and I'll go ahead and choose a different color, the a plus bi form. So these are in the a plus bi form where they have a term a that is completely real. So it's real plus a pure imaginary term. Not that big of a deal, at least with the scope of AP Precalculus, but it's good to know the distinction nonetheless. Okay. Zeros. We're going to go ahead and talk about zeros and how to find them in this lesson. And it's important to note that zeros of a polynomial function, if a is a complex number and we plug in a into a function and it gives us 0, if p of a equals 0, then we call that a zero of p, also known as a root. So sometimes you hear zeros called roots. Furthermore, if it's a 0, there will be a binomial, x minus a, that is a linear factor of the polynomial function p of x. In other words, for a function p of x, the zeros of p are values of x that make p of x equal to 0, okay? And I'll show you a concrete example kind of connecting these ideas further down below. All right, additionally, one idea that pops up in this lesson is this idea of conjugates. Conjugates. Can you say the word conjugate? Good. So complex conjugate theorem. What a conjugate theorem is that if p is a polynomial function and in one variable with real coefficients, and you get one imaginary solution, as a root, a plus bi, then there's going to be another, and I kind of like to call this BOGO, buy one get one free. They always come in pairs. The rule of 2 if you're a Star Wars fan. Okay, so a plus bi, if that's a root, then its conjugate a minus bi is also going to be a root of p. And this is also true for irrational numbers as well. Okay, so in other words, the roots or the zeros of the form a plus bi come in complex conjugate pairs. Okay, so for example, if I have -2 minus 7i, if this is a root of my polynomial, then its conjugate, which is -2 plus 7i, will also be a root. Okay, so note it's the same numbers, same two terms, just the second term is negative. or the opposite sign. Okay, so in this case, positive. Note, real zeros are known as x-intercepts because they appear on the graph. They touch the x-axis. Non-real imaginary zeros will not show up on the graph as x-intercepts. So let's go ahead and find some zeros in this next set of examples. And we're going to find zeros through a couple of strategies. You can factor, you can take a square root in order to solve, or if it's non-factorable and you have a trinomial, you can use the good old quadratic formula. Okay, so these are three strategies. Let's go ahead and look at example 1. Find all complex zeros of each function. Describe each zero as real or non-real. P of x equals x cubed minus 4x. Okay, so if I want the zeros, I'm going to set the function equal to 0, and then I'm going to factor. And I'll just add a little star right here, factor. And the first step always in factoring, step 1, is to find a GCF. So I'm going to take out a GCF here. I have x, leaving behind x squared minus 4 equals 0. Okay, so here I could dive into our second strategy, which is the square root property. I'll highlight that later, but I want to keep going with the factoring idea here. I have two terms, and I have subtraction with two perfect squares. This is what we call difference of two squares. I like to abbreviate that as dots. It's one of my favorite candies. So I can factor this. We get x times x minus 2 times x plus 2. And now I have broken it down completely. So here, in order to find the zeros, I'm going to set each of these factors equal to 0. I have x equals 0, I have x minus 2 equals 0, and I have x plus 2 equals 0. So I just set each factor equal to 0, and we're going to solve. So the first example, already solved. The second factor, I guess I should say, is solved by adding 2 to both sides, and we get x is equal to 2. And then our third factor, x is equal to negative 2 by subtracting 2 from each side. Okay, so we have here our zeros. The zeros are x equals negative 2, 0, and 2. And all of these are real. All of these are real numbers. Okay, that's example number 1. We're going to dive into example number 2. Again, I want to find the zeros, so I'm going to start by factoring. I take out the GCF, and I get x times x squared plus 2x minus 15 equals 0. And I'm going to factor this trinomial. I'm looking for factors of x squared, which is very simple, x and x. Factors of 15, negative, that are going to combine to give us a positive 2. So that's going to be a positive 5. And a negative 3. So all of these, again, set them equal to 0, and then we just solve. So x equals 0, we'll subtract 5 to get x equals negative 5, add 3 to get x equals 3. Okay, and then here's our zeros. X equals negative 5, 0, and 3, and then all of these are real. Okay, third example. In the third example, I don't have a GCF, but I can factor this, believe it or not, looking at it. I have x squared and x squared, and then I'm looking for factors of 80 that combine to give us 11. And this one's a tricky one. I have plus 16 and I have a minus 5. So here I'm going to go ahead and highlight the square root property of solving. So I have x squared minus 5 equals 0. I'm going to focus on this term first. So in order to go ahead and solve this, I can't factor x squared minus 5. 5 is not a perfect square, but I can go ahead and I can add 5 to both sides. Add 5 to both sides. And I get x squared equals 5. And then I'm going to solve this just by taking the square root of both sides. And I get x is equal to plus or minus the square root of 5. And there you have it. So those are two zeros. And again, this is an irrational. It's going to come in a conjugate pair. Okay, similar to complex, which we'll see here with the x squared plus 16 equals 0. So in order to solve this, again, I'm going to use the square root. I cannot factor this. This is not x minus 4x plus 4 because of the addition. This is sum of two squares. So I'm going to go ahead and subtract 16 on both sides. And hopefully as you do this, you see a red flag. You start to be afraid, very afraid. I want to go ahead and solve by taking a square root of both sides, And what I get is x equals plus or minus the square root of negative 16. We cannot have a square root of a negative number. This is imaginary. I'm going to go ahead and break this rational term up. Okay, and we have the square root of negative 1, which is I. So I have plus or minus the square root of 16 is 4, and then the square root of negative 1 is I. Okay, so there you have it. Here's our zeros. These are non-real, and these are real. All right. Whew. Okay. Hopefully you have brushed up a little bit on factorization, and now I want you to go ahead and practice this. Here's 2 examples, and give these a go, and then actually give this first one a go, and then I'll talk you through it here in a second. Okay, hopefully you paused the video. Did you pause the video? Good. So I'm going to set this equal to 0. There is a GCF. I do have a GCF. Leaving behind 2x squared minus 7x plus 5. And now I'm going to go ahead and factor this into 2 binomials. Okay? And you may get stuck here. A lot of students get stuck. And they're like, I don't know how to factor that. Just break apart your first term. So I have 2x squared. Well, that's going to be 2x and x. And then I have 5. 1 and 5. Okay? Nothing too crazy. So a lot of students kind of get paralyzed by thinking about it too much, paralysis by analysis. Just go ahead and this method is called guess and check, factoring by guess and check. So, and I'm going to do this wrong on purpose here for a second. So 1 and 5, well, I'll just place those there, and both of these need to be negative because I have a positive here. So negative times negative gives me the 5. And how you check is you're just going to multiply your outside numbers. So what's 2x times 5? Okay, that's negative 10x. And then what's negative 1 times x? Well, that's negative x. This gives me negative 11x, which is not what I want. So just go ahead and switch it. It's much quicker if you just take action and check rather than trying to paralyze yourself by thinking too much. Okay? So anyway, here's our factorization. 2x minus 5 times x minus 1. This gives us the 7x, right? 2 times 1 gives us 2. 5 times x gives us 5. So we have 7x. Okay, and then our factors, our zeros, are here. So x equals 0, 2x equals 5, which means x is equal to 5 halves, and then here x is equal to 1. So all of these are real. I guess I'll list x equals 0, 1, and 5 halves, and these are real. Did you get it? Good. Okay, let's go ahead and look at example number 2. Please go ahead and try this example, and I'll talk you through the solutions. All right, hopefully you paused the video. This one is hopefully more straightforward than the last. We'll take out a GCF, set each factor equal to 0, and then we'll move the 10 over to get x squared equals negative 10, which means x is equal to the square root, plus or minus the square root of negative 10. And we get plus or minus the square root of 10i. Okay, this is non-real. And then your 0 over here, that's 0, is real. Not too bad. Not too bad. Okay. Lastly, last practice problem for this lesson, and then I'll go ahead and break it here. This will be a 2-part video. Is the polynomial function r has a 0 of negative 2.6 plus 4.35i. Which of the following must be true? This complex number is a 0 of r. This imaginary number is a complex, or is a 0 of r. This imaginary number is a 0 of r, or other zeros of r cannot be determined from the given information. Go back up, hint, hint, go back up and read the complex conjugate theorem. Unpause me here in a second. Okay, hopefully you pause me. The answer to this is the other 0 is going to be the conjugate. If you know this imaginary number is a 0 of a function, well then it's going to have its conjugate be the other 0. Guaranteed, they come in pairs. Okay, and the conjugate just changes the sign of the second term. So our answer here looks like is C. All right, hopefully in this video you learned about how to find some complex zeros of polynomial functions from analytical form through factoring, solving, taking the square root property, and you learned about the complex conjugate theorem. All right, give me a thumbs up. Watch part 2 for learning about multiplicity of zeros and how we're going to go ahead and can graph some polynomial functions given zeros in end behavior. All right, see ya.